Matt, welcome. I just clicked the button to start things. And Caitlin, welcome. We're just getting rolling here. So first of all, happy Easter to all of you. I hope you had a good break. I want to start off with, I don't know if you remember, but we did have a 4.4 assignment and lesson before we left for break. And that was all about what? Concavity. Second derivative being positive indicated concave up. A second derivative that was a negative indicated concave down. Did anyone want to talk about any of those?
Could we go through number 33?
33? Okay. Okay. Let's see what we got here. I don't know if you can barely see it there on the screen, but it looks to me like it's f of x equals arc sine of x to the 4/5 power. Okay. So let's see what we got here. Let's take a look at that. Let me just write that down. F of x equals arc sine x to the 4/5 power. All right. Now let's go back to our thing. We'll create a little page here. Oops, let's change that to black. All right. So we know, let's see, I got to double check too. What were the directions? What are we trying to do here? So the problem says, if I look at the directions, find the points of inflection and discuss the concavity of the graph of the function. Okay, so points of inflection is second derivative. All right, so we got to find the second derivative of this. Let's see, we know that the derivative of the arc sine of something is equal to prime over square root of 1 minus u squared. So that was one of those derivatives we learned. Okay, so if I want to take y prime up above, I need to take the derivative of that x to the 4/5, put that on the top. So that would be 4/5 x to the negative 1/5 over 1 minus, see if I can get this cleaned up a little bit here. 1 minus u squared, which would be what? X to the 8/5. If you square, let's see, if you square x to the 4/5, it's x to the 4/5 times x to the 4/5, keep the base and add the exponents, x to the 8/5. Okay. So can we simplify this a little bit? That is 4/5 x, I'm sorry, 4/5, and then on the bottom we would have the x to the 1/5, so the 5th root. Maybe I just leave it as x to the 1/5. Okay, so x to the 1/5. And then we've got this thing. we should simplify this. So 1 minus, what can we do with that? Can we do anything with that? Can we bring that together? We could call that, yeah, there's not much we can do with that, is there? So square root 1 minus x to the 8/5. Well, except that we could rewrite it in fractional exponent form. So let me go back. So let's just write this as 1 minus x to the 8/5, and then all of that's raised to the 1/2. Okay. So simplifying it even further, we could bring that 5 on the bottom. From the, sorry, having little technical issues here. So on the bottom we've got 5 x to the 1/5 1 minus x to the 8/5 to the 1/2. All right. Or maybe I'd even be better off if I put everything on the top. Let's see. So if I did, maybe I'm just trying to find a better format here so we can take another derivative, because of course we have to take the second derivative. So let me see. 4/5 x to the negative 1/5 and quantity 1 minus x to the 8/5 to the negative 1/2. Okay, so there's my first derivative. My second derivative, okay, y prime, yeah, penmanship, having a little trouble with that today. So y, having technical issues here. Excuse me, guys. Get the keyboard off of here for a moment. At least on my end. Sorry, I took the keyboard off and now I lost my video output. Okay, I'm hoping you guys are still with me here. Okay. Somebody speak up. Are you guys still there?
Yeah, we're here.
Okay. Yeah, I lost my second screen where I keep track of all that. So anyway, y double prime. All right. So now we got to take the derivative of this thing over here. So power rule, negative 1/5 times 4/5 is what? Negative 4/25. Lower the power by 1. So it'd be negative 6/5. So that's the derivative of the first times the second. Whoa. My 6/5 didn't appear. Okay, so the derivative of the first times the second. Plus the first times the derivative of the second. Negative 1/2 times 1 minus x to the 8/5 to the negative halves. And then we have a chain rule times, wow, I'm out of space, times negative x to the 8/5 derivative. So negative 8/5 x to the 3/5. So the question is, when is all of that equal to 0? Okay. Yeah, you know what? I'll tell you what. This is going to take a while, and I don't want to. I think what I'm going to do is follow up with this. I'll tell you what. I'll either rewrite and send it out today, and or show it to you tomorrow morning. Okay? Because this is gonna. I don't know. This could be a lot longer than I anticipated here. Now, what happened? I'm trying to find my output. Wow. Okay, found it. Okay, I got my screen back. So anyway, sorry, but David, I'll keep going on this, and I just don't know if this would be a wise use of on the air time. So let's come back. Anybody else question from last time you want to look at? So either a follow-up email or first thing tomorrow morning, we'll look at that. Well, here's the topic for today. I think you're going to like this. Limits at infinity. I know it seems odd. Why would we return to limits after we've already gone well past application and we've been spending I don't know how much time on derivatives? But you're going to find this to be refreshing and I think quite easy to do. You can see there are three. I don't know if that's might be too tiny for you, but there are three objectives under there. Determine finite limits at infinity. Determine the horizontal asymptotes, if any, of the graph of a function. And determine infinite limits at infinity. So that's what we're going to look at. And let's see, I guess I should get rid of the pictures. So we have, there we go. We have full visibility now. So, so we take a look at this function here. It says use a graphing utility to graph this thing. Okay, so let me pull up Desmos. Yeah, do I have Desmos on here? Yeah, right there. Good. Okay, start graphing. And now let me quickly pull up my, as soon as it recognizes me. And this is the wrong example, isn't it? So let me just go back. What was that? So let me write this down. We have 2x squared plus 4x minus 6 over 3x squared plus 2x minus 16. Okay, sorry, I thought I had this ready and I didn't. Okay, so we have, interestingly, not the keyboard. So we have 2x squared, numerator, plus 4x minus 6. And then we're going to divide that by 3x squared plus 2x minus 16. And close parentheses. Okay, now the question, let me just go back real quick. So describe all the important features of the graph. Can you find a single viewing window that shows all of the features? Okay, I think we can see the major features of the graph right now. You can see what? That we have a couple of asymptotes. It looks like one, I don't know, it's -2 and -2 and some -2.5 approximately, and maybe +2. And it looks like what? We have, do you see how, I don't know if you can tell, but as I shove this to the right, do you see how the graph seems to be approaching a horizontal asymptote? That is, do you see how the graph never seems to go all the way to the origin as I shove it way out? Likewise, on the left, you see the same thing happening, the curve to the left. So this is, well, I mean, we've already dealt with vertical asymptotes, and we're going to be dealing with horizontal asymptotes. Let's see, what other feature of the graph can we look at here? I think you will also see that we, seem to have a point of inflection on the middle branch, somewhere, right about in here, I'm going to say. I'm just guessing, but somewhere right about in there, it changes from concave up to concave down. Okay, but it's the horizontal asymptotes that we particularly want to mention today. And let's see, I don't know, you probably can't tell here, but I'm going to just go out a ways, and let's just pick a point you can't really see. Yeah, well, you can see enough. You see I've clicked a point there, and what's the y coordinate? 0.696. Let me go a little further. 0.692. You see how it's below 0.7? Actually, just by looking at the equation, I know what that's headed toward. And that's what I want to show you. Here, let's come over here on this side. See again how we seem to be heading to 0.6 something as I go further and further to the left. Yeah. Well, I can tell by looking at, if you look over here at the left at the equation, that it's actually heading towards 2/3, 0.667, or 0.6 repeating. And we're going to learn a rule today for checking that out. Okay, so that's just a little introduction. So we're going to learn kind of a quick rule for dealing with some of that stuff. So let me go now. Take a look at, yeah. So you see how all these limits on this page in example 1 are x is approaching infinity. Yeah, all of these are approaching positive infinity. Do you see that? As x approaches positive infinity, what happens to 5 minus 2x squared? Well, 5, the limit of 5, has nothing to do with what x is. That's going to be 5. But that fraction, what will 2 over x squared be as x approaches infinity? So what happens when you square infinity? Well, it's just massively large, right? And what's 2 over a massively large number going to approach? Can all of you see that's approaching 0? And what's 5 minus 0? 5. You can see how we analyze that right here. The limit of 5 as x approaches 0, well, that's 5. And the limit of 2 over x squared as x approaches infinity is 0. And so the overall limit is 5. Okay, now look, take a look at this second question. What's the limit of 3 over e to the x as x approaches infinity? So e is what, about 2.7? So what's going to happen when we take 2.7 to an infinite power? It's going to get huge. And what's 3 over a huge number? I mean massive. It's going to be approaching 0. So no surprise. So just with a little bit of reasoning, you see what's happening whenever a denominator gets huge, this thing is approaching 0. It's getting closer and closer to 0, as in asymptotically. So what's going to happen in a problem like this one? Now we've got a little interesting problem here. If we look at the one in the book, here's the problem. So what's going to happen to that as x approaches infinity? Well, one way to solve this is divide top and bottom by the largest power of x. So in this problem, the largest power of x, I think you'll agree, is x to the first, right? I mean, there's 2 times x to the first minus 1 over x to the first plus 1. The largest power of x is x to the first power. So here's the rule. Divide top and bottom by the largest power of x. That's what they're doing right here. So do you see how they took the top, 2x minus 1, divided it by x, and they took the bottom, x plus 1, divided it by x? Well, I mean, what happens when you do that is you do the algebra, you wind up with you wind up with a separate limit. You know, what happens when you take the limit of 2? See what they did here. Do you see how they went from here to here? When you take 2x minus 1 and divide it by x, isn't that the same as 2x over x minus 1 over x? And what's 2x over x? 2. So 2 minus 1 over x. You see how they got this? And likewise on the bottom. You know, the bottom line is there's a cool shortcut. And I'm going to just show it to you. I'm just going to go right to it. Okay. So here are the guidelines for finding limits at plus or minus infinity anytime you have a fractional function, you know, a numerator and a denominator. And here it is. Number 1, if the degree of the numerator is less than the degree of the denominator, then the bottom is going to grow faster than the top and the limit's going to go 0. So if you're in a fraction and you got a higher power x on the bottom than on the top, then the bottom is going to completely outgrow the numerator, and it's going to tend to be, it's heading towards 0. On the opposite, number 2, if the degree of the numerator, let's go to number 3, if the degree of the numerator is greater than the degree of the denominator, then the numerator will completely outgrow the bottom, and you'll have this huge number on top over a smaller number which approaches infinity. And so they say it doesn't exist, but actually it approaches infinity. I know. Is that a limit? If something approaches infinity, is that a limit? We could argue that. Infinity is not a place, but we know it's huge. So just a matter of, you know, they could have said here the limit of the fraction approaches infinity. That's the same as saying there is no number limit. And then number 2, if the 2 degrees are equal, then the limit of the rational function is the ratio of the leading coefficients. Okay, so now let me just quickly go back to this problem. Remember I showed you this a little while ago? What's the highest power of x in the numerator of that function? It's x squared, right? And what's the highest power on the bottom? X squared. So here's a case where the 2 powers are equal. So what's going to happen as x goes to infinity? The answer will be the limit be the ratio of the leading coefficients. So as x approaches infinity, let me just write it here officially, the limit as x approaches infinity of that function is 2/3. So it's really cool. If the leading, you know, if the highest powers are equal, then all they got to do is look for the leading. So that's how I knew that graph was approaching 0.666, because I knew just by looking at it that the limit as x approaches infinity had to be 2/3. So it's a really cool, easy rule to apply. So let me just go over it again. Number 1, if the degree of the numerator is smaller than the degree of the denominator, then the limit's going to go to 0. as you're taking limits to positive or negative infinity. If the, number two, if the degree of the numerator is equal to that of the denominator, then the limit as x approaches infinity will go to the ratio of the leading coefficients. And number three, if the degree of the numerator is bigger than that of the denominator, then the limit's going to go to positive infinity or negative, depending on the sign. And you could either say the limit doesn't exist or it approaches infinity. So now we can apply this really cool rule and we can do a problem. Now here, well, yeah, let's skip this one right now. Let's go to this one. Okay, take a look at this function up at the top. And I'll just tell you, this relates to this word problem, so let's just quickly read it. Let f of t measure the level of oxygen in a pond, where f of t equals 1 is the normal, unpolluted level, and time t is measured in weeks. When t equals 0, organic waste is dumped into the pond and the waste material oxidizes. And of course, the level of oxygen in the pond is going to change. And here's the function, f of t equals t squared minus t plus 1 over t squared plus 1. Okay, so, I mean, let's go way to the bottom and just take a look at this. So can you tell me, based on the rule I just taught you, what's the limit of this function, t squared minus t plus 1 over t squared plus 1, as t approaches infinity? Do you notice that on top, the highest power is 2? On the bottom, the highest power is 2. They're equal. Therefore, the limit as t approaches infinity should be equal to the ratio of the leading coefficients, which is 1, 1. And 1 over 1 is 1. And, you know, that's the limit. And by the way, that represents 100%. So this is just such an easy, so even though we don't know anything about the curve, we take a limit like that quite quickly, and we don't even need to, you know, do a lot with pen and paper. Let's take a couple more here, finding limits and infinity. Take a look at A. Hopefully that's big enough for you. I know that's kind of tiny, but it says, this is example 8 in the book. If you got your book handy, that might help. What's the limit of 2x squared minus 4x all over x plus 1 as x approaches infinity? Well, notice the power on the top is higher. All right. So what does that mean? The limit's going to go to infinity. Sure enough, you look down here. Okay, answer to A. How about part B? What's the limit of that as x approaches negative infinity? Notice, again, this time, you know, I mean, this time we're going to have, okay, when you take on top, a negative infinity squared is going to be a positive. On the bottom, a negative infinity is going to be a negative. So we're going to have a positive over a negative. But again, the power on the top is bigger, 2. So it's going to approach, and see the answer is negative infinity. And sure enough, if you look at the graph, you can see this. What happens? You can't maybe see the, but as x approaches positive infinity, see how it really is. I mean, as we go to the right, that curve is going to get forever higher, and it's going to approach positive infinity. As we go to the left, as x gets further and further to the left, that curve is going to be going down. And so that really does match with what we just found out. Okay, let's look at a couple problems on the assignment. I thought, even though this is not on your official assignment, I think this is kind of a good activity here. The first part of the assignment says do a matching. Okay, so you notice over on the right here we have 6 functions. We have 6 functions over here. And then over here we have 6 graph. Which graph matches with the function? Well, how about if we take a look? I'll tell you what, let's look at each function. So first, take a look at this one. All right, what happens as x approaches infinity on that one? I don't know if you can see that, but it's 2x squared over x squared plus 2. Okay, so as x approaches infinity, what's going to happen? The powers on the top and the bottom are equal. Therefore, it should approach what? The ratio of leading coefficients. 2 over 1 is 2. Okay, so the graph to the right is going to approach. So, I mean, sorry. It's the trouble with a touch-sensitive screen. You touch it in the wrong place, and it creates problems. So anyway, what I'm trying to say is, in number 1, the limit, as x approaches infinity, of that f of x is 2. What's the limit as x approaches negative infinity for that same function? So now, if you plug in a negative, because of the squares on the top and the bottom, they're still going to be positive. Does everybody see that? So that 2 is going to be 2. Now, which curve, when you go way to the left and way to the right, approaches 2? Can you see that's this one? I mean, isn't that the only? I mean, I see. Well, it could be F too, couldn't it? Okay. So, how can we tell which one it is? Well, I mean, is it A or is it F? Well, couldn't we just plug in the, you know, on this one, the point what, 0, 2? And on this one, where it approaches 2 on both sides in F, F of 0 is 0. So plug in a 0, what happens? You get 0 over 2 is 0. So this one, can you see this one has to be F? So we're just doing a little detective work based on limits and common sense. So let me erase that other one. I mean, well, let's erase all of them now. Let's go to number 2. Okay, so here's the function. And by the way, what's the power of x on the bottom? I know it's an x squared, but it's under a square root. So in effect, that's x to the first. Okay, so when you do this rule about what's the highest power on the bottom, in this case it's 1. What's the highest power on the top? 1. So they're equal. So what are the leading coefficients? 2 on the top, 1 on the, so that one too, as x approaches positive infinity, is going to be 2. Okay, but how about if x approaches negative infinity? Well, on the bottom, when you square a negative infinity, it's a positive infinity. And when you take the square root of it, it's going to be positive x to the first. But on the top, when you plug in a negative infinity, so it's going to be negative 2. So here, let me just, so hopefully you follow this. So for number 2, the limit as x approaches positive infinity of that function is positive 2. The limit of that same function as x approaches negative infinity is negative 2, because you'll have the sign change on the top. So now which graph is approaching 2 on the right and negative 2 on the left? Bingo. Do you see how it's got to be that one? It's kind of a fun little detective game. Are you following my reasoning there? Let's do one more. Let me get rid of this writing here and we'll start over. Okay, so let's take a look at number 3 now. What's the limit of that as x approaches infinity? Well, top power, 1, bottom power, 2. So that's going to go to 0. Do you see that? So as x approaches positive infinity, Because the denominator is growing faster, that one's going to approach 0 on the right. Which one in the book seems to approach 0 on the right? Actually, it looks like B or D. But now, what happens as x approaches negative infinity? Well, it's going to be the same thing. It's going to go to 0, but it's going to be on the negative side. So which graph appears to approach 0 to the right from the top? And that would be, again, it looks like either B or D, right? Okay. So how can we find out which one it is, B or D? Well, how about we take a point? Like right here, that appears to be the point approximately 1, 2. What's f of 1 in this red circled function? 1/2. Nope, that's this one. You see that? 1, 1/2. So anyway, kind of a fun little detective game. I don't think we even gave you any official assignments here, but just from looking at what we learned today and a few basics about points, this is kind of a cool little function game. I don't know, that might even be an interesting idea for a possible quiz. Okay, let's go on to the ones where you will be assigned. All right, so it says, if possible, find the limit of h of x. Okay. So let's see. Let's take a look at number 13. So they gave us f of x, and they gave us, and they just said, all right, on the top you've got f of x, which in number 13 is what? 5x cubed minus 3x squared plus 10x, and divide that by x squared. What's the limit as x approaches infinity? Well, on top you would have an x cubed. On the bottom you would have an x squared. And obviously the top wins out over the bottom. So does everybody see that this one would be a positive infinity? Can you see that? All right, look at part. Here, let's go over to 14a. This time you have the function negative 4x squared plus 2x minus 5. Put that over x. Again, the top wins. But because the top is negative, it's going to go to negative infinity. Let's take a look at part B. Here, let's look at this one. Sorry, I know there's two B's. Let's stay on 13 now. So on the top, you've got 5x cubed minus 3x squared plus 10x. On the bottom, you've got x cubed. What's the highest power on top? X cubed. What's the highest power on the bottom? X cubed. Oh, they're tied. So therefore, as x approaches infinity, that thing will approach what? The ratio of the leading coefficients on top 5. So this is going to be a 5. I mean, let me just demonstrate that to you real quickly. If you're wondering where, I mean, am I way out in left field here? I'm going to just copy the function 5x cubed minus 3x squared plus 10x. And on the bottom, we've got x cubed. So let me just show you in Desmos. So on top, 5x cubed minus 3x squared plus 10x. And on the bottom, we've got x cubed. And remember, we're looking at the limit as x approaches positive infinity. So yeah, we've got two branches to the graph, but we're interested in is when x approaches positive infinity. And so do you see what's happening here? If I just take a point, you see how it's 20 comma 4.8. See, it's approaching 5 from the bottom. Let me go out even further. Okay, now we're out to 44. And you see how it's getting even closer to 5? 4.9. So what I'm trying to show you is that really does work. The limit of the curve is x. Where is that? What is that curve approaching as you go to x? X approaches infinity, and we found it was 5. Looks like it's going to do the same thing on the left, even though we didn't ask about that. All right. So now heading back. Let's do the last part of number 13. So if the function is 5x cubed minus 3x squared plus 10x, and it's over x to the 4th, what are the powers on the top and the bottom? The highest power on the top is 3. The highest power on the bottom is 4. And the bottom wins. Therefore, as x approaches positive infinity, that's going to approach 0. So anyway, it's that easy to apply that rule. Let's just see. Let's take a look at how about a problem like, well, let's take 15. I mean, real quickly, this one should be real quick. X, if you take the limit of x squared plus 2 over x cubed minus 1 as x approaches infinity, the bottom wins. That's got to be a 0, right? Okay. How about this one? Part B, 15b. They're tied, so it's got to approach the ratio of the leading coefficients, 1 to 1, 1. How about this one? The top wins, x squared to x on the bottom, so that's got to approach positive infinity. So the rule is actually pretty easy to use. Here, how about an exponential one? Let's take a look at 17a. Okay, as x approaches infinity, which power is higher? We have a 3/2 power on the top and a 2 power on the bottom. Which of those is bigger? 2 is bigger, right? So the bottom wins, so that's got to approach 0. How about part C? Whoops, how about part C? Which power is bigger? On top, we have a 3/2. On the bottom, we have a 1. 3/2 is bigger. Okay, therefore, the top wins, and it goes to, but because the top is negative, it goes to negative infinity. So, is that, hopefully that's making sense. All right, let's look at the next group. Again, these are just all find the limits. So let's just jump in and take, let's take another one here. Number 28. What's the limit of that as x approaches infinity? What's the highest power on the top? 2. What's the highest power on the bottom? Be careful. It's a 1, right? Because the square root of x squared is x. So we have a 2 on the top, a 1 on the bottom. That means it's going to increase without limits, so we should get a positive infinity here. How about number 30? On top, the high power is 2, right? Highest power on the bottom is 3, so the bottom wins. Whoops, I leaned in the wrong place again. The bottom wins, and so it should be approaching 0. How about 36? Get a little trig in here. Okay, the power rule is not going to, I got to think about this. Let me just see, I don't know if we can use the power rule here. So, as x approaches infinity, you've got infinity minus, well, the cosine of, the cosine of any angle, no matter how big, can only be what? Somewhere between -1 and 1. So it's going to be, from infinity, that's going to be pretty much non-effective. So we're going to have infinity. We do have tied powers on top and bottom. So it looks like that should be approaching 1. Let's take a look at that. Let's take a look at a graph of that. Right? Because the leading coefficients are 1, so it does work, I believe. Let's go back. Go back to Desmos. Okay, what was that problem again? X minus cosine. And that's all over X. Okay. X minus cosine X. And it's all over X. So as X approaches infinity, so you can see we've got this cosine variation, but sure enough, as X goes out to infinity, where are we? Oh yeah, we're real close to 1. Do you see that? A little bit above, a little bit below, but you know, we seem to be hovering and approaching it from both top and the bottom. So our answer of 1 does appear to be just fine. How about 35? That's a sine problem. So as X approaches infinity, so on top, you have to first take the angle and double it. So 2 times infinity is going to be a really huge angle. And what happens when you take the sine of a really huge angle? Again, it's got to be somewhere between 1 and negative 1, right? And on the bottom, it's huge. So we got somewhere between negative 1 and 1 divided by a huge number is going to approach 0. I don't know. Can all of you see that? So there are trig problems there too. Let me just see. We get a little more variety here. How about this one? Oh, need my pen. So what happens as X approaches infinity? Well, you see how X only approaches, there's only one value, there's only one occurrence of X in there, negative 5e to the negative X. So as X approaches infinity, that's going to be e to the negative infinity power. What does that mean? 1 over e to the infinity power. So that, in effect, it's going to be negative 5 over this honking number. Negative 5 over a honking number is I mean, that's a fraction that's so close to 0. So basically, this whole thing right here is going to be nothing, and 2 minus nothing should be 2. See, because this part, that doesn't change. 2 is 2. There's no X over there. So hopefully that's enough for you guys to get going here. Now I do want to show you a variation on the assignment too. And the variation, you look down here to 4.5, I have crossed out one problem from the core exercises. And 49 is still optional over here on the right, but skip number 47 from the core exercises. Otherwise, dig into the ones that, you know, the core exercises are your assignment except for that one problem. Questions? I see we're at about 50 minutes here, just worked out that way. So I'm going to get back to you on that either tomorrow or a little bit later today by email on that problem that was asked at the beginning of the class. This one here. We'll wrap that up. This would have taken too long. But so let me just sum up. I guess probably the most important page I showed you was this one right here. So for finding limits at plus or as X approaches either positive or negative infinity, if it's a fractional thing, all you got to do is use these 3 simple rules. If the degree of the top is smaller than the degree of the bottom, well, then it's going to go to 0. If the degree of the top is bigger than the bottom, then it's going to go to infinity. Watch out, either positive or negative, depending on the expression. And the middle one, if the 2 degrees are equal, then this rational expression will go to the ratio of the leading coefficients. That turns out to be pretty easy to use, not a lot of writing, and kind of a refreshingly shorter assignment for you. Questions? I hope you had a good break. And I look forward to seeing you tomorrow.
You want to go through that or talk about the test right now?
Yeah, let me see. I'm going to just, what I wanted to do after everybody else left is I just wanted to take a look and see what I have in my
Yep.
on my records. Yeah, let's see. I'm going to look on my other computer. Yeah, I have a feeling we may have to do this tomorrow, but let me see what I got.
No, that's okay.
I'm sorry you've had to wait.
Yeah, no, it's fine.
Yeah,
I just wanted to make
it's
sure.
always the problem when we do things a little out of sync, you know?
Yeah, no, that's fine. I just wanted to make sure it didn't get mishandled or anything, and like,
Well, you know, I can't guarantee that because I don't have the paper in hand at home here, but I don't think that should be a problem. But yeah, I guess I'll have to put that off till I see you tomorrow.
Okay.
Thanks, Neiman.
Yep. Sounds good. See you
Have a
tomorrow.
good one.